So in this section of chapter 2, we're going to be talking about specific sets. So we need to define what a set is. So a set is just a bunch of stuff or a collection of objects. And an element is just an individual object that's in that set, an individual member of that set. So if a set is well defined, then we have to be able to tell if an element is actually in that set. That's what it means to be well defined. In other words, it's not vague. It's not a vague description. It's a well defined description. So there are two ways well, there's multiple ways, but we're talking about two specific ways that we can describe a set. One is called where you just list the members of the set. It's called a roster or listing, roster method or listing method. So this first one, notice it's all the numbers that you would count with. If you started counting how many people are in the class, you would count with those numbers. So this is called the natural numbers. It's also called counting numbers, and those little dots are called the ellipsis. But anyway, so this is called natural numbers because it's the numbers you would naturally count with. Okay. Now notice this next set, we've added 0 and we've added negative numbers. Once you start talking negatives, those are integers. And it would be great if you noted integers like this with an I, but you don't. Okay, that's not how you show integers. Okay, you show integers with this Z because that I stands for irrational. So you do it with this Z, and they use the little double thing. I'm not a very good drawer. But anyway, that's the set of integers. Math people put the Z, and that's just the symbol for integers. Now, this next set is just the set of all the letters in the word math. Is it the same? Is that the same as this set? Notice it's got the M, it's got the M, it's got the A, yes, it is the same. It's in a different order, but that's okay. It is the same set. It's sort of like you had all your little girl's stuffed animals, and she put them all in a long line, and then you just grabbed them and put them in a bag she got lice, and you had to put them in the attic and get it. Can you tell I've had children? Put it in the attic and get it hot. It is the same set, still the same animals. It's just they're mixed up in a different order. Okay. So that's called the roster method or the listing method. You literally just list them. Notice what's at the end of each one of these. It's those little bracket things, right? The little brackets. So that's at the end of the list, okay? Because those brackets, that's how you know it's a set. So those brackets are also at the end of the set builder notation. So those brackets go on any set, whether it's in roster or listing method, or it's in set builder. Okay, but all set builder notations have a few other things involved. Okay, so they're going to have this X. So that is going to be that you're going to say that little bracket means the set of. So the set of all X, and then that little slash mark means such that. Okay, so anytime you read set builder notation, you will say the set of all X such that, and then you'll have the rest of it. Okay, X is an even natural number. Okay, oh, can we write that? X, the set of all numbers, the set of all X, such that it's an even natural number. So natural number, it's the stuff we count with, right? So it's not going to be negatives. It's not going to be fractions, okay? It's just going to be all our even numbers. So we're going to write it as a list. 2, 4, 6, 8, ... Notice I have little brackets at the end. Okay, that's using the listing method. So let's do this next one. Okay, so the next one, that X is the set of all X, The slash means such that. So the set of all x such that x is an n. What is an n? That was our natural number, right? That's our natural number. So x is an element of natural numbers. So we know we're talking about our counting numbers, right? And x is greater than 3. So x is bigger than 3. So you would read that. Notice there's not a single word in there, okay? But you would read it, the set of all x, such that x is a natural number and x is bigger than 3. So it's all the numbers we count with that are bigger than 3. So what would we start with? We'd start with 4, right? So it's going to be 4, 5, 6, 7. We keep going. Notice I put those little brackets at the end to show that it's a set. Okay, so you will be doing this. You will be writing. I will give you a set that's written as in a list, and you'll have to write it in set builder notation. I'll give you set builder notation, and you have to write it in the listing numbers. Okay, so the trap is you're not going to repeat any numbers or letters when you're listing them. Okay. So here's an example. The set of letters in the word geometry. So you're going to just list them. Okay. Notice that I have an E here, but I also have an E down there. I don't write it twice. Okay. So I'm not going to have the same number of letters as I do in the word geometry. In set builder notation, you would have the little x with the slash, right? The set of all x such that, and then I just wrote out x as a letter in geometry. Okay. So here's another one. The set of all natural numbers. Remember, natural numbers are numbers we naturally count with. So 1, 2, 3, 4, 5, 6, 7. But it has to be less than 9. So it's going to start with 1 and it goes up to 8 because it's got to be less than 9, right? So set builder notation, you've got different ways you could say it, but it all would have x. Whoops, sorry about that. They all would have this part, x, the set of all x, such that, and now we're going to have x is a natural number, so that's that part, and x is less than 9. Okay, some people would say x is a number, is a natural number less than 9, but this would give you, geeky brownie points by writing it with no word except the word and in there. And you don't even have to put the word and. If you really want to be geeky, you can just put a comma in there. That means the same thing. All right. So how do you know if two sets are equal? They are equal if and only if they contain exactly the same elements. Notice, doesn't have to be in the same order, but they have the exact same elements. Okay, so we have this thing called one-to-one correspondence. Okay, so here's the definition of one-to-one correspondence. If the elements in the set P can be paired, and S, can be paired so that for each element of P, there is exactly one element of S, and for each element of S, there's exactly one element of P, then the two sets are said to be one-to-one correspondence. So I like to think of that as we have our popsicles and we have our students. We've got 3 popsicles and 3 students. If I handed the popsicles out to the students, every student would get a popsicle. We would have no leftover popsicles. And every popsicle gets a student. We don't have any leftover students, right? So it's 1-to-1. You don't have more students than popsicles. You don't have more popsicles than students. They're the exact same amount. Okay, that's called one-to-one correspondence. So we want to find out if the following sets can be placed in one-to-one correspondence. And I was supposed to cover up those answers. Anyway, So here's the first one: 1, 2, 3, 4, 5, and I'm going to see if they correspond to MNOPQ. Notice there are 5 in this one and 5 in that one. So yes, it can be placed in one-to-one correspondence. Now this one has 13 letters in it. If you count A to M, that's 13 letters. This one has 10. So we've got some extra, we've got extra letters. We've got 3 extra letters, right? So that would not be one-to-one correspondence. And then X, there is a set of all X such that X is in the letter, is a letter in the word mathematics. Notice I wrote down what that was because we can't have any repeats, right? So there's just 8 and 1 through 11. So no, but if you counted these letters, there's 11 letters there, okay? So that is the trap that we talked about. Trap. You can't have any repeats. There's only 8 letters in our set, in that first set, okay? So now this one. I weren't supposed to see that either. Anyway, okay. So ignore those answers. Okay. So we're supposed to exhibit all the one-to-one correspondence between these two sets. We've got A, B, and C, and 4 swimming lanes. Okay, 4 swimming lanes. So I'm going to take. Go. Here's lane 1, and I'm going to put A in lane 1. We'll call that Al. So we put Al. We'll put Al in that swimming lane. Let's call him Alfred. How about that? We'll put Alfred in the first swimming lane. All right. So if Alfred is in the first swimming lane, then that means in the second lane, I only have 3 choices, right? I could put Bubba. I could put Clyde. I could put Dan. Okay. So there's my 3. Okay. So if we put so now we know what's in lane 2. Now let's go to lane 3. If I can get my pen working. Okay, look in lane 3. So if we put Bubba in lane 2, that's only going to leave us with Clyde and Dan for lane 3. If we put Clyde in lane 2, then that leaves us with Bubba and Dan for lane 3. If we put Dan in lane 2, that only leaves us Bubba or Clyde. Make sense? And then let's go to lane 4. So here's our lane 4. So notice you've got Alfred in the first one, Bubba in the second one, Clyde in the third one, then Dan's the only one left. But if Dan was in that third lane, now Clyde's the only one left. So you could follow this. So I could follow here, and that tells me everyone, that's the first the first way that we could put those 4 people in our lanes. Here's another way. There's the second way we could put people in the lanes. Here's the third way we could put people in the lanes. Here's the fourth way we could put people in the lanes. Okay, so when we have Alfred in there in the first lane, then I'm trying to get this to go back, and it's not. Anyway, when we have Alfred in the first lane, then we have 6 ways. There's 6 ways that we could put Alfred, Bubba, Clyde, and Dan in the lanes if Alfred is in the first lane. Well, what happens if we put, let's put Bubba in the first lane? So if we put Bubba in the first lane, that changes everything up, right? So but there's still 6 ways that we could do it, because if Bubba's in the first lane, then instead of having Bubba here, we're gonna put him, we're gonna stick him up right there. Okay, so that's how those 2 switch. Okay, So we've got 6 ways. And then we could put Clyde in the first lane. Then we could put Dan in the first lane. So there's 6 ways if we had Clyde in there, and there's 6 ways if we had Dan in there. So our total is 24 ways, right? Because we have 6 ways for Alfred, 6 ways for Bubba, 6 ways for Clyde, and 6 ways if we had Dan in that first lane. So total is 24 ways. Now, notice that if there's 4 of them, right? We had 4 people. If you multiply 4 times 3 times 2 times 1, notice what you get. You get 24. So find how many. Let's look at C. Find the number of one-to-one correspondence between 2 sets with 5 elements. In other words, we had A, B, C, D, E. We had Elroy. So Elroy was in there, and we have a 5th lane. So how many could we have? We could do the exact same thing, but if you notice with this, you would say 4, 3, 2, 1. Well, if you have 5, you just add that 5, 4, 3, 2, 1 and multiply them all together. So there'd be 120 elements or 120 ways that you could put those 5 people in those swim lanes. Okay, so this is actually called the fundamental counting principle. If one event can occur in M ways and a second can occur in N ways, the number of ways the 2 events can occur in sequence is M times N. That's what we're coming up with, okay? So let's do one. Let's do some examples. You have an access code for a car's security system consists of 4 digits. I don't know if you've ever had a car that you didn't have to have a key to get in the door. You just punch in a little code and it opens the doors for you. That's what we're talking about. Okay. Each digit can be 0 through 9. In other words, you can't have a 10 as one digit, right? So 0 through 9. How many access codes are possible if you can only use each digit can be used only once and you cannot repeat it? So that means, let's see, we've got 4, right? They said we got 4 digits. Okay. So the first one, how many digits do we have to choose from out of for the first one? So here's our first one, and we have 0 through 9. So that means we have 10 digits we can choose, right? For that one. Well, then let's say we put a 7 in there. Okay. Well, once we put a 7, notice it says you cannot repeat it. So once you put a 7 here, you can't use it. So now instead of 0 through 9, I've got 0 through 9, but I don't have that 7. So I have 9 that I can choose from for this next one. And then for the third one, I've already used, let's see, 7, and I've used 8. So now I can only use 0, 1, 2, 3, 4, 5, 6, and 9. So I only have 8 possible ones. So I would have 10 times 9 times 8 times 7. I'm going to erase these guys so that doesn't confuse you a little bit. So my answer, if I multiply all those together, is going to be 5,040. Okay. Now, what if each digit can be repeated? So I chose 7 this time, but that means I could choose 7 again. So if it can be repeated, then I still have my 4, but it's going to be 10 every time. 10 times 10 times 10 times 10. So that gives me 10,000 choices. Look how many more choices you have just because you didn't repeat. What if each one can be repeated, but the very first digit can't be 0 or 1? So this very first one can't be 0 or 1. So that takes out of the 10, we can't do 2 of them. So we can only use 8 there. Okay. But then For the next one, I can use 10, right? So then the next one would be 10 and 10 and 10. So we multiply that together, we get 8,000. I love those. I just think those are so much fun because I'm a geek. So, if I think they're fun, they're going to be on the test. All right. So, how many corresponding one-to-one correspondence are there between two sets with 4 elements? Remember, we did that already up here. 4 elements are 4 people that are going to swim in 4 lanes, right? We said it was 24, and we said the easy way to get it is 4 times 3 times 2 times 1. It's 24. There is a shortcut way of writing that, and that is 4 with an exclamation point. That's called a factorial. Factorial. Okay. So if you had 8 elements, you had 8 people swimming and 8 lanes. That would be 8 times 7 times 6 times 5 times 4. So that's 40,320. Again, shortcut method is 8 with an exclamation point. What about n elements? N elements, well, that's going to be n with an exclamation point. Now notice this is the math geek way of writing it. Your n, so if n was 8, then the next one would need to be 7, right? So 8 minus 1 would give me 7, and the next one will be 8 minus 2, which would give me 6, all the way until we get down here to 1, right? 8, 7, 6. Notice I'm subtracting 1, then I subtract 2, then I subtract 3. So that's how we get our factorials, okay? All right, so equivalent sets. So 2 sets are said to be equivalent if and only if there exists a one-to-one correspondence, okay? So they have the same number of elements. Notice that equivalent doesn't mean the same, okay? That does not mean the same. The same is the exact same elements. Same means the same elements, okay? If it's equivalent, that means there's just a one-to-one correspondence. So you have Alfred going into lane 1. You don't have Alfred in one set and Alfred in the other set, okay? So equivalent has that little squiggle. That little squiggle instead of an equal mark, okay? If it was the same, it would be an equal mark. Okay, here is a special word, cardinal number, and a cardinal number is the number of elements in the set. You count how many elements are in the set. This is hint from test. It's not a difficult concept, right? You just count how many elements are in the set. You write down that number, okay? But students miss it because they do not recognize the symbol for the cardinal number. Notice the symbol. It's in parenthesis A. So here's my A. Okay, there's my set, and I'm going to ask this. This right here says, what is the cardinal number of that? So A, B, C, D. There's 4 letters in there, so the answer is just 4. It's that easy. What's the cardinal number for this next set? Cat, dog, parakeet, hamster. There's 4 in that one too. So the cardinal numbers are the same. So these guys would be considered equivalent. They're not equal, but they would be considered equivalent sets. Okay. What would be my symbol that says how many members, what's the cardinal number for this set R? And let's count 1, 2, 3, 4, 5, 6. So I have 6 in there, so the cardinal number 6. Now look at this V. I don't have anything in there. So the cardinal number 0. I don't have any elements. Okay, this is called the empty set. It could also be called the null set, and it can be written with a 0 and a slash through it. Okay, so there's 2 ways of writing the empty set. You could write it like this, literally a set with nothing in it, or you could write it like that, a 0 with a slash through it. But you cannot write it like that. You can't have both of them, okay? So this, if you write that, that's going to be considered wrong. That is not, that's the empty set of the empty set. That's the set of the empty set, which is weird. Okay, so you can't write it like that. You can either write it like this or like that. Both of those mean empty set. What about this guy? Does that mean the empty set? It's got a zero in it. Okay, no, it's a set with zero, the number zero in it, right? Okay. So two sets are equivalent if they have the same cardinal number. They have to have the same cardinal number, not the same elements. Okay. So let's see if these guys, which one of these are equal and which ones are equivalent. Let's check out A and B. Notice A has ABC in it and B has XYZ. So are they equal? No, they're not the same. They don't have the same elements, but they are equivalent because they have the same number of elements. So now let's check out A and C. A and C. Well, those guys, they're not equal. They don't have the same elements. And they're not equivalent because one has 3 and one has 4. So both of those are no. So A and D. Here's A, ABC. Here's my D, BAC. Notice BAC, I could rearrange that and get the same thing I started with A. So those guys are equal, and when they're equal, they are also called equivalent. They have the same number, but they have the same cardinal number, but they also have the exact same elements in there. So let's look at B and C. B is XYZ. C has 4 in there. Okay, so they're different elements and there's a different cardinal number. So both of those are no. B and D. B has 3. D has 3. Notice they're not the same. So if they're not the same, they're not equivalent. Excuse me, they're not equal, but they are equivalent. So equal has to have the same exact elements. Equivalent has the cardinal numbers are equal. So C and D, there's C, here's D. They do not have the same elements, and they also don't have the same number of elements. So that's the difference between equal and equivalent sets. Okay. Let's take a break, and then we'll finish up this